Alrighty, hello, hello. This is time for the next lecture, I think the lecture number 2. This is one that's going to be over section 3.2, which is going to cover Rolle's theorem and the mean value theorem. But before we get to that, we are going to go over the homework that we had. So let's jump on right into that. We had number 17, and that was f of x is equal to 4x squared minus 6x. Okay? And we're supposed to find the critical numbers. Okay? So, quick refresher over here. What are the critical numbers? Well, the critical numbers, well, two things. Either A, the derivative at some value doesn't exist, but the original value did exist. So, you had f of x existing, but f prime of x does not exist. And this is usually where we have a cusp. And B, the other type of critical number, is where f prime of x equals 0. This is where we're going to have slopes of 0, which are horizontal slopes. And this tends to generally correspond to mins and maxes. There's something else it can be as well, but we'll hit that in a section or two. But for right now, mins or maxes. So here we go. So let's see what the critical numbers are. So if I look at f of x is equal to this, let's look at f prime of x then. F prime of x is going to be 8x minus 6. Okay? So for critical numbers, part A, f prime of x does not exist. Alright, are there any values that this function is discontinuous on? And the answer is no. There are no discontinuities for the derivative. Alrighty. What about B? F prime of x equals 0. Well, all I have to do is set the derivative f prime of x equal to 0. So 8x minus 6 equals 0. 8x equals 6. X is equal to 6 over 8, which is equal to 3 over 4. Okay? So for this problem, the critical numbers are just x equals 3/4. And that is going to correspond to a min or a max. Alrighty? So far so good. Now let's go to the next one. So the next one, let me clear this, was number 18. So 18, a little more interesting. We had g of x is equal to x minus root x. First thing I'm going to do is change that. I'm going to rewrite this into x minus x to the 1/2 so that I can actually take the derivative. So when I take the derivative now, we'll get g prime of x is equal to derivative of x is 1, and derivative of x to the 1/2 is going to be 1/2 times x to the negative 1/2 using the power rule. Okay? Now if I wanted to rewrite that to gain a little more insight into it, it would be 1 minus 1 over 2 root x, because that's what x to the negative 1/2 is. It's the root x in the bottom. Okay? So first thing I want to do is to find my critical numbers. I want to look at where g prime of x does not exist. Now, this, as I've been saying a few times, this only applies for when g of x does exist and g prime of x doesn't exist. If I look back up here at the top, g of x does not exist for all x less than 0, right? Because it's the root. If I plug any negative value in here, I'm going to get something that's imaginary. So all values of x that are less than 0 don't exist for the original function. Okay, so I don't have to worry about those in my critical numbers down here. if it doesn't exist in the original function, it's definitely not going to exist in the derivative, since the derivative doesn't exist. But I do need to look to see if there are any values that the original function, was fine at, but the derivative has a discontinuity. And it turns out that if I look at this expression now, not only do I have to worry about x values that are less than 0, now I have to worry about values where it's equal to 0. So in this case, I actually have a discontinuity at x equals 0 that was fine in the original expression, because root 0 is just 0. The problem is when it's in the bottom. So I've got, that is a discontinuity, and we've talked about that. That is probably a cusp. It's going to be kind of a one-sided cusp, because on the other side it's imaginary values, but it's going to approach a cusp as it heads up from the positive side. Okay? And then the second thing I need to do to look for critical numbers is when g prime of x equals 0. Well, when does this equal 0? All I have to do is set the derivative equal to 0 and solve. So 1 minus 1 over 2 root x equals 0. Okay, that's going to be 1 equals 1 over 2 root x. I'm now going to cross multiply. When I do that, I'm going to wind up with 2 root x equal to 1, root x equal to 1/2, x equals 1/4. I'm squaring both sides. Okay, so that is one of the critical numbers. So now, if I want to list the critical numbers occur at x equals 0, that's a cusp, and x equals 1/4. That is some sort of min or max. And that's it. That's number 18. Alrighty, let's go on and take out the next ones. Okay, so number 27 was f of x equals x cubed minus 3/2 x squared, and we're given that the domain is going to consist of values from -3 to +1, and we are supposed to find the absolute extrema. So the absolute min, and the absolute max. So the way that we do that, first we need to find the critical values. So first off, let's take the derivative. F prime of x is equal to 3x squared minus 3x. Okay? And then to find the critical numbers for part A, we look for places where f prime of x doesn't exist. Are there any areas? Nope, that's a polynomial, so there are no discontinuities. We don't have to worry about that. Part B, f prime of x equals 0. Well, let's set it equal to 0 and solve. So that's going to be 3x squared minus 3x equals 0. 3x times x minus 1 equals 0. X equals 0, and x equals 1. Okay? So those are two critical numbers we found. So when we're looking for absolute extrema, we go through 4 steps. First step, find the critical numbers. So the critical numbers we just found are at x equals 0 and x equals 1. Second step, we plug in those values into the original function. So f at 0, well, when I plug 0 into the original function, I get 0 back. And then f at 1, I get 1 minus 3/2, so it's going to give me a negative 1/2. Step 3, we plug in the endpoints to the original function, so f of -3, When I plug in negative 3 here, I'm going to get negative 3 cubed minus 3 halves times negative 3 squared. This is going to be negative 27 minus 27 halves. So this is going to be negative 54 halves minus negative 27 halves, which is going to equal negative 81 halves for negative 3. The second endpoint is at f of 1. Well, we already have that, right? That is at negative 1 half. So last step, step 4, we'll do the absolute max. The absolute max, what is the largest of the values between negative 1 half, negative 81 halves, and 0? Well, 0, right? And that occurs at x equals 0. And then the absolute min is going to be, well, the lowest value of all these is by far negative 81 halves, and that occurs at x equals negative 3. So that's where you have your absolute max and your absolute min for the function. Alrighty, pretty good, not too bad so far. Let's move on to the next one. So the next one was 31, and 31 was g of x is equal to 6x squared over x minus 2. And the domain that we're looking at is between negative 2 and 1. Alrighty, so first things first, I need to take the derivative, and this is going to be a quotient rule. So it's going to be the bottom times derivative of the top. Derivative of 6x squared is 12x minus the top, 6x squared, times derivative of the bottom, which is just going to be 1. And all of that over the bottom squared. So x minus 2 quantity squared. Alrighty. I'm now going to distribute this and kind of simplify things. So 12x times x is 12x squared. 12x times negative 2 is negative 24x. And then minus 6x squared. All that over x minus 2 quantity squared. Okay? So 12x squared minus 6x squared is going to be 6x squared minus 24x, all that over x minus 2 quantity squared. Okay? Now, here's the deal. The original expression had a discontinuity at what? X equals 2, right? But that is not inside of our domain, so we don't have to worry about that value. Inside of our domain, looking at this expression right here, are there any discontinuities? So are there any places where g prime of x does not exist in this domain? So answer, nope. The only discontinuity is at x equals 2, and so we don't have to worry about that. So there are no discontinuities. Okay? Now, next thing, part B, for the critical numbers, is when g prime of x equals 0. Alrighty, so we set the derivative right here equal to 0 to solve. So I'm going to have, let's see, 6x squared minus 24x all over x minus 2 quantity squared equals 0. This looks like a mess to solve for, except it's not so bad, because a fraction is equal to 0 when the top is equal to 0. So to find the values that make this expression equal to 0, I just have to set the top equal to 0. So 6x squared minus 24x equals 0. 6x times, what is that going to give me? X minus 4 equals 0. So x equals 0 and x equals 4. Alrighty, I have my critical numbers now. Alright, so to find the absolute extrema, I'm going to have to go to the next page. So clear this. So step 1. Well, let me get my original function. The original function is, let's see, g of x is equal to 6x squared over x minus 2. And the domain was from -2 to 1. Alrighty, so step 1, I found my critical numbers. The critical numbers were at x is equal to, what was it? I've already forgotten. 0 and x is equal to 4. Well, I forgot to look at this because x equals 4 is also out of the domain, so I don't have to worry about that. All I have to worry about now is the x equals 0, which is included in this domain. So I find f at 0. Well, f at 0 is going to be 0 over -2, which is 0. Step 3, I'm going to plug in the endpoint. So f of -2 is going to be, what is that? -2 squared is 4 times 6 is 24 over -4, which is -6. And f of 1 is going to be 6 over -1, which is also -6. Okay? So step 4, to find the absolute extrema, I get my absolute max. Well, the absolute max is where I get a 0 for my y value, so that occurs at x equals 0. And the absolute minimum occurs at y equals -6, which happens at x equals -2 and x equals +1. So there you have it. I've got my lowest value at x equals 0 and my highest values at -2 and +1. And that is that. Alrighty, ready for the next one? Here we go. Let me clear the screen. Let's see, so this next one, oh yes, the trig function. We need more of those. So we had, for 37, f of x equals sine x. And the domain that we were given is 5, I can write a 5 pi over 6 to 11 pi over 6. Okay, so first things first, find the derivative. F prime of x is, what's the derivative of sine x? Cosine x. Alrighty. So now, for the critical numbers, part A, are there any places where f prime of x does not exist? No, there are no discontinuities with cosine. That is 100% continuous. Part B, where does the derivative equal 0? Well, where is cosine of x 0? Well, if I look at the unit circle, cosine is the x value. Where on the unit circle is the x value 0? Well, that occurs right here at pi over 2 and here at 3 pi over 2. But the only one of these that lies within the domain is 3 pi over 2. So that occurs at x equals 3 pi over 2. And that's it. That's all we had to do. So now I can move on to find the absolute extrema. So step 1, the critical numbers. Well, that occurs at x equals 3 pi over 2. That's it. Step 2, I see what the y value is for that value. So 3 pi over 2. What is now I have to look at my original function. So I've got f of 3 pi over 2 is sine of 3 pi over 2. So 3 pi over 2 is right here. What is that sine value? Well, the sine value is the y value. So what is the y there? Well, that's -1. Okay. Step 3, to find the extrema, I need to plug in my endpoints of my domain. So I've got f of 5 pi over 6. Alrighty, so 5 pi over 6 is right here in the unit circle. And I'm looking for the y value, since that's the sine at that point. And that y value is going to be 1/2. Because this point is at -√3 over 2, 1/2. Okay, and then I need the second endpoint, and so the second endpoint is going to be f of 11 pi over 6. Well, 11 pi over 6 is located over here. What is that y value? That is a -1/2. Okay, so time to move to the very last step, step 4, the absolute max. Well, what is the largest y value between -1, -1/2, and +1/2? Well, +1/2. And where does that occur? At x equals 5 pi over 6. Okay, absolute min. Well, that is at -1, and that occurs at x equals what? 3 pi over 2. And that's it. That is all that we needed. So hopefully the homework went well. If you have any questions, just feel free to email me or swing by for a one-on-one chat via Zoom. I will have all that information out in an email to y'all. So, all right, we are now ready to tackle section 3.2. Clear this, and here we go. Okay, so we have section 3.2. We're going to start off with Rolle's theorem. So Rolle's theorem, we're actually going to write it out and then we'll decipher it. If I have a function, if f is continuous on interval a, b, I have to have that, then if f of a equals f of b, then there must be a c in open interval a, b such that f prime at c equals 0. Alrighty, that looks terrible, but it's really not. What this is saying, first off, we have f is a continuous function on the interval from a to b. We sort of need that so that we don't have some crazy behavior going on with jumping all over the place. So if it's continuous, we can't pick up our pen at any point. So it's a nice unbroken function. Then if f of a equals f of b. So what is f of a and what is f of b? Well, f of a is the y value at x equals a, and f of b is the y value at x equals b. So this is the y at the left side, this is the y at the right side. So I've got some function. I'll go ahead and I'll make one up. I'll call this a, and this b, and I have some function where the y value, if I could draw correctly, for a, which is f at a, and the y value of b, which is f of b, if they are the same value, then there must be some value c, so some value between a and b, such that the slope at that point equals 0. The slope is a horizontal line, so somewhere between a and b, there's a point at which the slope is 0. And I would say that point probably lies somewhere around here. We'll call that C. That is a horizontal line at that point, assuming I can draw the functions, which I can't, but in my attempt to draw it correctly, if you have point A and point B having the same y value, and the function's continuous, there has to be a point at which the slope is 0. A, B, if I start here and at exactly the same y value, so this is my f of A, this is my f of B, if they are the same, then there's some point between these two that has a horizontal slope. It has a min or a max, in other words, because it's continuous no matter how I travel between. I can do whatever I want, but because it's continuous, at some point, at least one point, there is a value between A and B at which the slope is 0. And you can see that for every single one of these. I've got a horizontal tangent here, horizontal tangent here, horizontal tangent here, 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 and here. No matter how I try to get from point A to point B, if point A and point B are at the exact same slope, the same height rather, there's at least one point in between that has a slope of 0. And that makes perfect sense once you kind of see it drawn out. There's no way to get from point A to point B if they're at the same y value without having one point at which there is a slope of 0. Okay? So we can now use that and actually do a problem. So let's try that. Let me clear the screen. Okay, so let's say that we have, maybe as an example, function f of x is equal to x squared minus 3x plus 2. Okay? Now, I want two y values that are going to be the same. Turns out, when you think about it, I can figure out this function where it has two y values that are the same when I find the solutions to this function. Because when I talk about solving, normally I set it equal to 0 and I solve, right? I do some factoring, and when I do that, I'm looking for the x values that when I plug in will give me a y value of 0, right? So all I have to do is solve for x here. So I set this equal to 0. X squared minus 3x plus 2 equals 0. And that's going to factor nicely into what? Well, x minus 2 times x minus 1, which means x equals 2 and x equals 1. At these two locations, when I plug the x values in, I get a y value of 0. or f of x equals 0. So f of x equals 0. Alrighty? So that's what I needed. This says that Rolle's theorem, so Rolle's theorem says that if f at 1 equals f at 2, there is some value c between x equals 1 and x equals 2, such that f prime at c equals 0. Okay? So now let's lock that down with some calculus, because I can actually solve this. Let's see, so all I have to do is take the derivative of my f of x, so f prime at x is going to be the derivative of this. What's the derivative? Well, it's going to be 2x minus 3. If I set that equal to 0, so 2x minus 3 equals 0, 2x equals 3, x equals 3 halves. Ta-da! There was a value, 3 halves, that was between x equals 1 and x equals 2, such that the slope was 0. Isn't that cool? Rolle's theorem is a good theorem. All you have to do is, typically, you need to find two y values that are the same. You do that by finding solutions to the function, and that locks down that y is 0 at those positions. At some point between those two values, then, there's a value where you have a horizontal slope. How do you find that to verify? Well, you just set the derivative equal to 0 and solve. At that location, it is between your 2 points that you had that had the same y values. So kind of neat that it works that way. Alrighty. Hopefully that it went fairly well. Sometimes you will be given endpoints on a domain that will have the exact same y value, and if that's the case, you don't have to go through this process of solving. You just have to make sure that your 2 points have the same y value. If they do, then you just set the derivative equal to 0 and solve and verify that there was a value between the two that had a slope of 0. Let's do one of those real quick. So let me clear the screen. Clear the screen. Alrighty, let's say that we have, let's go with something fun. Let's do f of x equals x to the 2/3 minus 1, and we'll have the interval will be -8 to 8. Can we use Rolle's theorem to guarantee there is a value between these two values that has a slope of 0? Well, first off, let's see what the y values we get when we plug this in. Well, if I look at -8 to the 2/3 minus 1, well, -8 to the 2/3, I can do that a couple of different ways. First thing I'm going to do is, because this is, if I rewrite this, this is -8 squared and the cube root of that, right? So I'm going to square this. It's going to give me 64, and then the cube root of 64 is 4. And it's going to be the exact same thing if I do the cube root of 8 squared, because it's also going to give me 64. So both of these, so f of -8 is equal to, I'm going to have 4 minus 1, which is 3, and f of +8 is 4 minus 1, which is 3. So between these, they have the exact same y value. Between -8 and 8, there's at least one point that has a horizontal slope. Okay, so how can we find that? Well, we're going to take the derivative. So f prime of x is going to be the derivative of x to the 2/3 is going to be 2/3 x to the negative 1/3, and then the derivative of -1 is 0, so we don't have to worry about that. Okay, now all I have to do is set this equal to 0, so f prime of x equals to 0. Well, that's just 2/3 x to the negative 1/3 equal to 0. Well, that's not too hard to solve for because the only value that x can be that's going to make this equal to 0 is at 0, so x equals 0. Now, does 0 lie between -8 and 8? Yes, it does. So, Rolle's theorem works. Yay! Alrighty, so we'll do some practice with Rolle's theorem. It doesn't come up a whole lot in calculus or in later mathematics, but you might see it a time or two. So that's Rolle's theorem. Now let's move to the mean value theorem, which is a more general case of Rolle's theorem. So let me clear this. Okay, so the mean value theorem, let's figure this one out. The mean value theorem, which I will for henceforth call the MVT because it's less of a mouthful. So here we go. If f is continuous on AB, we've seen that before already. And here's another one that we need to state. Differentiable on AB. And it doesn't have to be, you don't have to include the endpoints for that. So if it's continuous on AB and differentiable on AB, all the points within AB, then there exists a C in open interval AB. So somewhere between AB there is a value C such that, all right, here we go. F prime at C equals f of B minus f of A over B minus A. Okay, so hopefully this looks a little familiar right here. What is f of B minus f of A over B minus A? Well, it looks bad until you think about it for a second. A and B are two x values, so f of A and f of B are the corresponding y values. Just for absolutely no reason, I'm going to call A x1 and B x2. And if that's the case, then f of A is going to be y1 and f of B is going to be y2. So now if I rewrite this the way I've got it labeled up top, this becomes y2 minus y1 over x2 minus x1. What is this? Well, this is the slope formula. This is rise over run. So what is this saying then? Well, if I have a continuous function that is differentiable, then there always exists a value between A and B, so some value in between x1 and x2, such that the slope of that value, the slope at that value, whatever it is equal to the slope between A and B. So what does that mean? Well, if I think about what this is saying that if I have some values, I'll just make some up. We'll say A, maybe the value is here, that's your f of A, and maybe B is somewhere over here, that's B, and this is f of B. Okay, so the slope is this value right here. This slope is my f of B, y2, minus f of A, y1, over B minus A. That's what that is. Now, the mean value theorem says that there is an AC, at least one C, some value in between A and B, that has a slope that matches the average slope between A and B. So, if I have this function here, if I have rather the two endpoints here at A and B, and a function that moves between them, maybe the function does this. What this says is that there is at least one point at which the slope is the same as the average slope. So that would be maybe something that looks, maybe the average slope is here, assuming I can draw, which I can't. Right there is the tangent line to this function, and that matches the average slope. Okay? Just like when we were doing Rolle's theorem, there's no way that I can get from point A to point B with a function without having the same slope as the average slope at least once. That would occur right here, and even right here. So to get from point A to point B, the function, since it's continuous and differentiable, has to have at least one point, some value between A and B, that has exactly the same slope as the average slope. Okay? No matter how I go, since it's continuous from point A to point B, it has to match that at least once. So this, we're going to work an example, maybe two, and then we're going to work the application of this. Out of all the theorems that we've covered so far, the mean value theorem is the one that actually gets used in the real world. I won't say frequently, but it is used. You will see this one pop up from time to time. So let's do an example first, and then we'll go to the actual application. So then we clear the screen. For the example, let's say that we have f of x is equal to x cubed plus 2x plus 4. And we're going to give the domain from -1 to 0. Okay? So the first thing that we're going to do is figure out what the average slope is. So I've got my A and my B. Now I need f of A and f of B. So f of A is going to equal -1 cubed plus 2 times -1 plus 4. So I'm going to get -1 minus 2, -3 plus 4 is 1. And f of B is going to be 0 cubed plus 2 times 0 plus 4. Well, 0 cubed is 0 plus 0 plus 4 is equal to 4. Okay? So now I set up f of b minus f of a over b minus a. Well, that's going to be 4 minus 1 over 0 minus negative 1, which is going to be 3 over 1, which is 3. Okay? So, the MVT guarantees there is at least one value between x equals negative 1 and x equals 0 that has a slope of 3. That's it. That's what the MVT guarantees, is there is at least one point between negative 1 and 0 that has a slope of 3. Okay? That doesn't seem very satisfying until you see the real world application. So I'm just going to go ahead and jump straight to that. This video is getting a little long anyways. Let's have some fun. So here we go. Let me clear the screen. And let's look at this. So this is where it kicks in the real world. This is where you use the MVT to give a speeding ticket. Alrighty, so here we go. Before we jump into the problem, we need to do a little background. We need to talk about rate. So you remember the good old formula that relates distance, rate, and time? We had dirt, where that is distance equals rate times time. Dirt. Okay, so that means that the rate something is going is equal to distance divided by time, right? Okay, well, when we talk about miles per hour, so mph, well, that is just distance, miles per hour, time, distance over time. Okay, now here we go. This is where it gets fun. This is going to be a lot of words, but it'll be worth it. So a police officer is at mile marker 10 on the interstate and clocks you going 70 mph, so 70 miles an hour, and which is the speed limit. I'll go ahead and write that out, because some interstates it's more or less. Okay, now he clocks you at, I need to say this, which is speed limit. He clocks you going 70 miles per hour at 7:30 a.m. You're trying to get to your 8 a.m. math class, we'll say. You're not going to make it, but that's okay. So a second police officer at mile marker 50 clocks you going 70 miles per hour at 8 o'clock a.m. Now, if the two clocks, the two watches, clocks, timestamps, whatever, are synchronized, do you get a ticket? So, we're going to go back through it real quick. So we have a police officer at mile marker 10. They use their radar and find out that you're going 70 miles per hour, which is the speed limit, at 7:30 a.m. Second police officer at mile marker 50, again, uses radar and finds out you're going 70 miles per hour, the speed limit, at 8 a.m. If the two clocks that they're using, the two timepieces, one said 7:30 a.m., the second time was 8 a.m., if those two are synchronized, do you get a ticket? The answer is yes, you do, if they know the MVT. Okay, let's see why. So I'm going to clear the screen. Clear the screen. Alrighty, so first thing we want to do is we want to calculate the average speed. Okay, well, how do we get that? Well, average speed is a rate, and we know that that is distance divided by time. So the distance, well, you were at mile marker 50 for the second one and mile marker 10 for the first one. That's miles. And then how much time had elapsed? Well, the time was 8 a.m. for the second one. This is going to be a little bit weird because I have to do this in hours because it's miles per hour is what I want. So I'll do a little scratch work. How many hours? Hours from 7:30 to 8. Well, that's half an hour, right? So 1/2 hour. So I've done going 40 miles in half an hour. Okay, so 40 miles over 1/2 hour. Well, that converts into 80 mph. That is the average speed. Now, by the MVT, since driving is continuous, you cannot pick your car up and put it down at a different location. Since the average speed was 80 miles an hour. There was at least 1 point, not poing, point at which you were going 80 miles per hour. It doesn't matter that when they both clocked you on radar, you were doing 70 miles an hour. Since the average speed you had to travel to get from point A to point B was 80 miles an hour, there was at least 1 point in between those 2 points at which your rate had to be 80 miles an hour. So they can give you a ticket for doing 80 miles an hour, even though they both clocked you at doing 70 miles an hour. Now, this was actually a thing several years ago. I say several. I want to say one of my students was telling me about this 4 years ago, in Atlanta, where you have all the different tolls on the highways. So you're driving down the interstate, you pass through one toll booth, and then you get to the second toll booth, and the toll booths are synchronized. It calculates the average rate of speed that you had to go to get between toll booth 1 and toll booth 2. If that is over the speed limit, you get mailed a ticket, even though you were doing the speed limit at the tolls themselves. This has since been challenged and overturned in several locations across the country because it relies on both of the clocks have to be synchronized. If there's any discrepancy between them, you can't guarantee that the person had to be doing over the speed limit. But if you synchronize the clocks, mathematically, you had to be doing over the speed limit. So that is just a very cool application of using the mean value theorem. Alrighty, I hope you enjoyed it. Let me give you some homework and we will call this one done. So let me clear this. Okay, so this is going to be from 3.2. We're going to have, let's go with number 12, 17, 21, and 42. And let's star 12, 21, and 42. Alrighty. Thank you. I will see you in the next video. Have fun with the homework. Bye-bye.